Today, we're going to show you how you can set up a closed-loop brain state-dependent stimulation experiment using the bossapp research. The goal of closed-loop brain state-dependent stimulation is to synchronize the timing of brain stimulation to an ongoing, individual, natural, neural oscillation of interest to achieve longer-lasting effects and improve the intervention results. A setup for closed-loop brain state-dependent stimulation should provide a reliable near-to-real-time EEG data access, but also raw data saving option for offline data analysis. This can be achieved by using actiCHamp or actiCHamp Plus amplifiers in combination with TurboLink, which streams data in ultra-fast fashion with minimal jitter. Also, the setup should process the EEG data in real time and with high accuracy. To this end, we use the bossdevice research by Sync2Brain, a millisecond resolution online signal processor based on a Simulink real-time data model. The bossdevice research continuously monitors the neural oscillations of a target brain area in real time. It estimates the upcoming phase values based on the present status, it searches for a desired brain state and, once found, sends a standard digital output to activate an external intervention, like a TMS stimulator. To easily manage all these functionalities and to control the experiment in a user-friendly way, we use the bossapp research. To show you how to get started with the bossapp research, we run a simple experiment to monitor an individual natural occipital alpha activity during resting state with eyes closed and target the moments of peak phase. We start by connecting the equipment. And preparing our workspace in BrainVision Recorder. Here, remember to select the option actiCHamp plus TurboLink as your amplifier, to select 5 kHz as sampling rate, and to choose the data client transfer rate of 1 kHz with packetting option in the TurboLink web console. We prepare the participant by lowering impedances and then start the bossapp research. First, we connect with the bossdevice research by clicking on the disconnected button. We then start the internal algorithm, clicking on the Start button. If the EEG amplifier is already active, for example in monitoring mode, the EEG amplifier light will turn green. If not, it will be at first red. Next, we navigate to the EEG tab and its configuration sub-tab to define our brain area of interest. We create a new configuration and edit the spatial filter weights table. We enter the name, the physical channel numbers, and filter weight values only for the electrodes of interest, in our case, 3 occipital channels. The algorithm inside the bossdevice research will apply a spatial filter by a means of Hisior transformation on this subset of channels to optimize the signal-to-noise ratio. You can check the spatially filtered signals in the Spatial Filter Data sub-tab by clicking on the Switch button. We now move to the Protocol tab to define our experimental condition. We create a new protocol and add a new condition. We define our frequency band of interest by ticking the corresponding Enable box. For our experiment, we select only the alpha band. We then define the target phase to be detected by double-clicking on the relative frequency target field and editing the values in the dedicated pop-up window. To detect phase peaks, we enter the predefined value of 0 radians with a bit of tolerance. We then define the digital outputs by double-clicking on the trigger configuration field. In our experiment, we use 2 BNC ports to activate the stimulator, as well as to save trigger information in our EEG data offline. We select the respective port number boxes and adjust the TTL pulse length in the pulse width field to match our EEG sampling rate. In our experiment, we do not add any delay before sending the triggers. We continue and define the total number of trials for our condition by modifying the number value in the cycles field accordingly. Depending on your research question and stimulation protocol, your number of trials may be different. To make the experiment even smoother, conditions can start automatically if the auto start option is selected. Also, external markers coming in via the dedicated LPT port of the bossdevice research can be used to initiate or stop a condition. In our experiment, we do not use these options. The next step is very important. We navigate to the Spectrum tab to evaluate the natural peak frequency in the occipital alpha band to synchronize the intervention accordingly. We record at least 3 minutes of data, and then click on the Update Spectrum button to generate the power spectral density and related signal-to-noise ratio plots. By hovering over the power spectral density plot, we can note the natural peak frequency value. Next, we move to the Oscillations tab and click on the Tune Filters button to change the peak frequency for the alpha band frequency filter. To check if the data model is properly tuned around the natural peak frequency, we select the alpha frequency band and switch on the Enable button. We should here observe a sawtooth pattern in the phase graph. Here, we can also set a minimum oscillation amplitude value by clicking on the y-axis of the interactive amplitude graph. This means that if the amplitude goes below thresholds, the bossdevice research will temporarily hold back sending any digital output. We are now ready to start our experiment. We navigate back to the Protocol tab, select our condition, and click on the Start button in the Protocol Control section. The bossdevice research will start and continue till the total number of cycles or trials is run. To evaluate the performance of the online signal processor, we can switch to the Phase Estimation Accuracy tab, select the alpha frequency band in the Oscillation section, and click on the Update button. The resulting polar histogram plot gives us an indication of how accurately the data model in the bossdevice research estimates the target phase trial by trial. Good performance would result in a polar histogram plot centered around 0 radians. If the estimated accuracy is not good, we can further optimize our experimental parameters. For example, by checking that the originally detected peak frequency in the alpha band is indeed correct. Furthermore, we can tune the detection of some noise activity available in the Artifacts tab. For example, we could set thresholds for eye blinks and range artifacts by clicking on the y-axis of the respective interactive plots. When the detected activity goes above thresholds, the EEG clean signal light will turn red, and the bossdevice research will temporarily hold back sending any digital output.